Hi, good morning. Welcome to the 17th lecture on topology. Today the topic is going to be dense subsets in a topological space. Okay, so we will get started. We will explain the significance in the beginning, and again we will explain the significance toward the end with reference to functions. And as usual, we'll look at a lot of examples on the way. So all of you in your course in real analysis, you must have seen what is known as density of rationals. What did it say? You give me any two real numbers with a less than b, there exists a rational number q so that a is strictly less than or less than b. This is same as saying, let's look at an open interval ab, then there exists some r. This is in q, right? So we want to understand why we want to look at such objects. Okay, what is the significance of this result? You might have proved it or you might have just learned it, but what is the significance? The significance of this is something very interesting. That is, suppose I give a real number alpha in R. See, for example, alpha could be e to the power pi, or much worse, pi to the power 1 by e. So maths allows us to define such objects, but they are very complicated numbers. But what we are happy with is natural numbers, integers, and rational numbers. This we are more comfortable with this. So what this says is, you give me any epsilon positive, right? I can find a rational number r so that r approximates alpha within epsilon distance. Do you understand that? So this epsilon is pre-assigned, so it could be something like 10 to the power 200, as small as that. Then I can find a rational number which is so close to alpha, and so for all practical purposes the rational number will do for me if I am very seriously interested in measurement, right? So that is the advantage of this. So a dense set simply means an arbitrary element of the set can be approximated by an element from the dense set. This is the intuition. Okay, let us try to first reformulate this a slightly different way. Notice that AB is a typical open set. It's actually basic open set in R with usual topology. With it, usual topology, right? So this implies that give me any non-empty open set, okay, then U intersection Q is not empty. Is that clear? Because it is non-empty, therefore there is an x in U, therefore there is an epsilon positive, so that x minus epsilon x plus epsilon is contained in U, and this is an interval, this is your A, this is your B, therefore x minus epsilon, okay, x minus epsilon less than or less than x plus epsilon. There is a rational number R. That's it. Okay, you understand? So this allows us to make a very general definition of a dense set in a topological space. Okay, so I will first write down the definition and explain the intuition behind that again. So let x tau be a topological space and D a subset of x. Then we say D is dense in x, actually x tau with respect to the topology. It's very important, but if the tau is understood, you will simply say in x, in short. Okay, yeah. For every non-empty open set, U in tau, we have U intersection D is not empty. Do you see that? There we said n interval AB intersection Q is non-empty, and hence any non-empty open set intersection Q is non-empty. That's exactly what we are saying. Do you understand this definition? Okay. Now what does this try to say? Okay, so think of this an example. This is my favorite example. Okay, suppose this is my space X. Okay, and these are my let me just go back. Adding expert. Yeah, I thought I had chosen this. Okay, these are my elements. Okay, so my D is this kind of points, right? Now what does this say? I want to say this D is done. That means you give me any non-empty open set, however small it is. Okay, then it will always trap an element of D. Okay, I am going to give a real life analogy which many students from Bengal may love to hear. Think of this X as a pond. Okay, and these things as fish. Sorry, fish in X, the fish in the pond, right? And these blues are nets, small nets. Okay, however small net you cast, okay, here what you are going to do, okay, you will always find, and it will always catch a fish. That means the the fish in this pond are dense. No matter how small a net you cast, you will certainly catch a fish. Okay, that's what it means. Okay, pause, review, proceed. See, I love this definition, okay, instead of the standard definition you find in textbooks, okay, because you can see the intuition is very good with this, okay, because in a given a topology, what are the most primitive concepts? They are open sets. So we are defining something, okay, as a dense set in terms of the open sets. Namely, give me any non-empty open set, it should intersect the set D. That's it. So you see that, and you also have a picture, right, that immediately catches the intuition behind the concept of dense sets. Okay, now let us investigate. There are two investigations I want to do now. Okay, the first observation. So let D be dense. What does it mean? X is a topological space with a given topology, therefore D is with respect to that. Okay, the dense with respect to that topology. Right. Now start with any arbitrary element capital X in X and let U be any open neighborhood of X in X. Right? You understand? Now what do I know about, since that means in particular X belong to U, therefore U is not empty, and its U is a non-empty open set, but D is dense, therefore what do I know? I know that U intersection D is not empty. Right? Now let's try to understand. You gave me an arbitrary element X in X and U to be any open neighborhood of X, then U always intersects D. So what is the relation between X and D? I'm sure all of you know that, right? X is an adherent point. And what is X? X is an arbitrary element. Therefore, every element of capital X, the topological space, is an adherent point of D. Have you understood? Yes? That's it. So, what have we concluded? So we have concluded if D is dense in X, then every element X in the space capital X is an adherent point of D. That's the conclusion. What is the next question I would like to ask? The converse. Conversely, let every x be an adherent point of a set. I don't know whether it's dense or not, a set D in X. Then question is D dense in X? Yeah, but that's easy. Why? To show U is dense in X, what do I have to do? Let U be non-empty open set. Then I have to show U intersection D is not empty. I have to check this, right? But U is non-empty. What does that mean? Since U is non-empty, that means there exists X in U. That means, right, now X is an arbitrary element of capital X, and I know it's an adherent point of D. That's our hypothesis, right? Therefore, X is an adherent point of D by hypothesis. And U is an open neighborhood of X. Therefore, U intersection D is not empty. Right? I want to show U intersection D is non-empty. I have shown that. So, what do you think I have concluded? So, this is the fact we have concluded. Okay. D is dense. Just subset D is dense in X if and only if every X in capital X is an adherent point of D. Okay. Pause, review, proceed. You see that geometry is very clear with this definition. You see that? Yeah, very good. Now let's come back to the standard of thing. Many of you might have learned, because all teachers and textbook love this definition because you can chant it like a mantra. Okay, but it may not allow you to get. In my experience, I have seen people who learn density only using the definition which you are going to give. They do not know how to work with the density in the hypothesis. Okay, if the dense subset is given in the proof, they do not know how to exploit that hypothesis because intuition is missing. Anyway, this is all sales talk. Let's get to it. Now let D be dense. Okay, now this is the second observation. Okay, suppose this is dense. Okay, I should change the color, right? Okay, so observation 2, let D in X be dense. Okay, then what did we know? Then by fact 1, call this is fact 1. Fact 1, what do I know? Fact 1, okay, implies every X in capital X is an adherent point. Okay, that means what? Every X in X is said that X belongs to D closure, because do you remember? Right, any adherent point of the set belongs to the closure of the set. Yeah, this is closure of D in X tau. Right, you see that? And that means what? But this is every X, and D closure is a subset of X. But we are saying X is a subset of D closure, therefore D closure is X. So what have we concluded? Conclusion: if D in X is dense in X, then D closure is X. Do you remember this definition? Most often this is what you learn. Yeah, right. Now what is the next thing? As usual, converse. What is the converse? If D in X is such that D closure is X, then we want to conclude D is dense in X. Yeah, to conclude D is dense in X, there are various ways of proving, but we can show if D is dense in X if and only if by fact 1 every point is an adherent point of D, right? But that's very clear. Since D closure, let X belong to capital X, but X equal to D closure, this implies X is an adherent point. D, right? You understand that? That means every X in X is an adherent point of D. Therefore, by fact 1, D is dense in X. Okay, pause, review, proceed. Yeah. So what have we shown? Now we have shown the following are equivalent. Theorem: let X tau be a topological space, let D be a subset of X. Then the following are equivalent. What are they? 1, for every U in tau, U non-empty, we have U intersection D is not empty. These are definition of density actually. I could have simply said D is dense in X. And second, okay, every X in X is an adherent point of D. Third, closure of D in X, that is D closure equal to X. Okay, this is what we have proved. Do you find the proof very easy? Isn't it easier? So which one is easier? You can see obviously 1 and 2 are easy. Okay, 1 gives an immediate thing. I have D to imagine some X and some points D, then D is dense, meaning draw very small any open set inside, then it will have one element of D, at least one element of D, right? And the next one says you give me any X, it has to be an adherent point of the given set. And okay, the third one is more. It's your choice. Okay, but most often this is the official definition. Okay, which I do not very much in favor, which I am not in very much favor. Okay, now it's time to look at examples. So we had already seen the first example, Q, and this I didn't say, but you know, these are dense in R, of course with usual topology, right? Okay, now let's look at X with discrete metric, not discrete metric, discrete topology, right? Then now do you remember what are the simplest open sets? Suppose D is dense. Okay, assume this D is dense in X. Then what do I know? It should intersect every non-empty open set. And what are the simplest open sets in X in a discrete metric discrete space? All singleton X, right? These are all in tau discrete. That means singleton X cross D must be non-empty. But there is only one element. That means give me any X in capital X, this means X must be in D, that is my D must be all of X. Do you understand this logic? It's fun. You see that? I am not simply saying the only subset. You know, it's not a verification. Usually the textbooks and teachers will say the only dense subset of a discrete space is the full set. Then verify. But what we are doing is assume D is dense. We then arrived at that D can be nothing other than X. That's lovely. So what is the next example you should think of? X with indiscrete. Right? Now suppose D is again dense in X. Okay? Then what does it mean? D intersection any open set U in indiscrete topology, okay, should be non-empty. But the only non-empty open set is X. Therefore D intersection X should be non-empty. But D is a subset of X, therefore this is D. Therefore D is non-empty. So what have we concluded? Isn't it beautiful? Now we arrive at the result. You see that We are not simply saying somebody is saying any non-empty subset of indiscrete space is dense. No, we arrived at it. Okay, so we have shown any non-empty subset of an indiscrete space is dense in the space. Okay, so pause, review, proceed. This is the third example, right? Now let's look at the fourth example. What should be the next one? Let us say with all these examples are the same, so I will just do one of them and you can do the other. Okay, for example, n with cofinite topology and r with co-countable topology or r with ray topology, yeah, and few others possibly, right? See, in all these things, the basic trick is if you take two non-empty sets, okay, two non-empty open sets in topology, this tau is tau, it may be cofinite, co-countable or ray, okay, whichever example you are looking at, okay. Then U intersection, they are non-empty, of course. Then this is not empty. This we have seen it. Do you remember that? Yeah? Right. I don't want to again go through this kind of argument. You should be immediately able to work out the argument. If it is empty, then U intersection V is empty, therefore U convolution union, V convolution must be all of X, etc., etc., etc. Okay, you can do that. I don't want to waste my time. Okay, in this case is much easier. Okay, so what happens? Therefore it says take any non-empty open set U in this in tau, then U is dense in tau. I'm just saying here in the topology because I don't know which is the space now. You all do you agree? Why? Because you start with any non-empty open set V, then U intersection V is non-empty. That means, okay, every non-empty set V intersects my D, namely D equal to U. That's it. You follow that? Yeah. Again, you should know in all these cases we have already found out what are the adherent points. Okay. See, this is how you should learn, consolidate your understanding. Don't just stop here. This proof is okay, but you should also remember we had already done what are the adherent points. Points of any non-empty open set. Okay, in our earlier thing when we talked about adherent points, we looked at these things. Then we have seen every point of the space is an adherent point, right? So by fact 1, this must be dense. Are you sure? See, this is how you should consolidate. Go back and forth. Make sure, even if you get confused, don't worry. Okay, and please believe me, do not, okay, try to think along with me and understand. Do not worry about whether I can recall. Don't worry. You begin to think, you will see you can think on your own, and that too very fast with practice. Okay, please do that. Okay, what should be the fifth example? Of course, R with VIP topology. Of course, VIP is 0 as usual. Okay. Now, what are the simplest open sets? You know them. They are either 0 or they are of the form 0, x, where x is any real number. If x is 0, it's only singleton x. You understand? Now, can you immediately think of D, a dense subset? Every open set must intersect D. Come on. All of you can think. Yeah. Singleton 0. Right? Why? Because any non-empty open set will already contain 0 that intersects D. Therefore, this is dense in R with VIP topology. Yes? right. Notice that this is just an observation. Just if D is dense in some space, this is something x tau. Okay, general case. Okay, and suppose okay D is contained in du. Let us say D is contained in E, then E is also dense. So if something is dense, any superset, any set bigger than the D which contains D will also be dense. That's because U intersection D is subset of U intersection E, therefore it's non-empty. Okay, where U is non-empty open set. Right, therefore I can generate lot more open sets. Okay, right, you start with therefore any set A in R which says that 0 contains A, then A is dense. Here, do all of you agree with that? Okay, now as exercise I will leave the outcast topology to you. Okay, okay, this is exercise, you do it. Now let's look at another observation. Suppose x tau 1 and tau 1 and tau 2 are topologies on X, and tau 2 is finer than tau 1. Right? Now suppose D is dense. And now you see that I cannot simply say X. I have to say in X tau 2. Okay? In the topology space X with tau 2, where tau 2 is a bigger topology. What can you conclude? Why? Because suppose you start with any open set U in tau 1 and U is not empty, then U is again a non-empty open set in tau 2, because tau 1 is contained in tau 2. Therefore U intersection D is non-empty. Yeah? Therefore this is clear. On the other hand, the converse may not be true. Right? If you have any doubt, the converse is not true. Just now we saw an example. How many of you can do? That is, if D is dense in X tau 1, is D dense in X tau 2, where tau 2 is finer than tau 1. That's not true, because I can take tau 1 to be in discrete topology and tau 2 to be discrete topology, and X has at least 2 elements. Then any proper non-empty subset will be dense in tau 1, we saw, but that need not be in tau 2. Do you follow that? So if A non-empty not equal to X, then A is dense. Where? In X tau 1, but not dense in, this is in discrete, and X with discrete topology. Yeah? Right. That is why it is going to be very interesting. Okay? This observation, which is a slight digression, is to impress upon you the following fact. Now, I don't know, remember the example number, I think 7, right? Example 7. Let's consider R with the lower limit topology. Alright? Okay. Yes? Right. Now, consider R with the usual topology. By the way, just 1 second. I'm sorry for the disruption, digression. This just shows you, okay, when I am lecturing, I keep thinking. I'm not trying to recall. You see that? Okay, I'll come to example 7 later. Do you remember we saw R with the ray topology and R with the usual topology? And as you know, tau ray is coarser than tau u. right? But we have seen any open set of the form A infinity, which is in Tavrez, this is dense in R with Taure, but is not dense. You follow that? Because you're using indiscrete discrete, okay, is all right, but you should also learn some more concrete example. I just thought of it just now. We have proved it, do you remember? So one should make use of it. See, this is how I learn. Keep thinking back and forth, okay. Do not think that I ought to finish it very linear fashion, okay. Allow yourself to be what you call uh, explorative, okay. You should be ready to experiment. Okay, now come to example 7. So now I am going to tau L and R with tau U, and we know tau L is finer than tau U, and we know Q is dense in. So what should I say? I may not expect Q to be dense in R with the lower limit topology, but actually it turns out to be is surprise. In spite of the fact this is much larger topology. That's very easy, because what are the simplest open sets in lower limit topology? They are of the form A comma B, right? But I know there is a rational number R, or I already know A intersection B intersection Q is not empty, right? But A intersection B intersection Q is contained in A intersection B intersection Q. This is not empty, right? Therefore I proved this is not empty. Do you like that? Yes? Very good. Now the last example, that's I think enough. Now let's look at R2 with the order topology. Okay, R2 with the usual topology. Okay, or Rn with usual topology if you want. But I will stick to R2 so that I can draw pictures. Now let us look at, we know Q is dense in R with usual topology. Therefore I want to know whether this is dense in here. That is Q squared. Yeah. Now what are the typical open sets here? Okay, simplest basic open sets. Okay, either disk or the squares. Okay, this is with respect to D2 metric, or this is with respect to D max metric, and we know both the topologies are the same, induced by D2, D1, D max. They are all the same, so it does not matter which one I use. Now if you look at this, let's look at this example. This is my U. Okay, that you all follow that, so I can assume it is of the form something A to B and C to D. Okay, this is A comma C, and this is B comma C, this is A comma D, and this is B comma D. Okay, this is B, this is C, this is D, and this is A, this is B. Okay, now what do I know? I know in between there is a rational number R, in between C and D there is a rational number S, therefore this number R comma S will be inside this. Are you following? A less than R less than B, and similarly A less than S less than D, R and S in Q. That's because density of rationals there in R with the usual topology. Now the R comma S therefore belong to this C comma D, etc. Do you understand that? Yeah. Therefore what do you think I have proved? Any open ball with the D max metric contains a point with rational coordinates. Both the coordinates are rational. So same thing with Rn. Okay, please pause, review, proceed. So this is the last example. That was not the last example. Now let's look at R2 with order topology O. Okay, and this I had already done in the order topology second lecture, so I will just be quick. Okay, the basic open sets here are like this. If I take a point a comma b in R2, the basic open set will be of this kind. I am drawing a big picture. A, this is b minus epsilon, this a, b plus epsilon, and this may be your ab. So only in the y direction it moves. You understand? Therefore you can see q is not dense. Q squared is not dense in R2, because if I take a not in Q, now this is a basic open set. Okay, you understand? Therefore anything in this basic open set will be of the form a comma a t. Okay, and a is irrational and t can be anything. T, if you want, I can choose to be rational also, it does not matter, but the first coordinate is not rational. Therefore there is no point in this basic open set where both the coordinates are rational. Therefore Q2 is not dense in R2. Do you understand that? Look at this basic open set which I have defined using your intuition. Now can you think of this exercise? Think of dense sets which involve Q and R minus Q, etc. Set of rational, irrational, some combinations. It's very easy. Just look at this picture. Okay, you can create. I'm not asking you give this and asking you to verify. You see that creation is always very important. Okay, now before ending the lecture, I will start with the significance of dense sets. Importance. As I first said, okay, the first observation was if D is dense and x tau is same as saying, okay, any x in x can be approximated. This is intuition by an element of D. In other words, think of any open set, we think of those as neighborhood, right? Therefore that means in any neighborhood u of x, okay, there is a y in D so that y is near to x. You understand that? So I have D, okay, I have an open set U, or I have an open set U, or I have an open set U. Okay, I can always find an element of, sorry, this is x, this is U, I can always find an element of D, and so on. Okay, in case of metric spaces, suppose X is a metric space and D is dense in the metric topology. So what does that mean? That means you give me any x in capital X. Let us look at Bx 1 upon n. This is an open set, non-empty open set. Therefore it should intersect D. That means there is a y here. Therefore what does it say? So for every x in x and for every epsilon positive or 1 by n, okay, there is a y in D so that distance between x and y is less than epsilon. That means you can approximate any given x by means of an element from the dense set so that the distance between them is as small as you want. That's what we say, that dense sets approximate any arbitrary elements, because D may be set of nice elements with which we are comfortable. Therefore, okay, any arbitrary element of x I can, okay, approximate it by means of an element from the dense set D, which is our convenient sets. And second, this is this function theoretical thing. Okay, this will be the last example that I will solve. Suppose x tau is a topological space, and suppose f and D is dense in x, and assume f and g are real valued continuous functions. okay, or maybe even complex valued, okay, or it can be taking values in a metric space YD, or if you know what is meant by Hausdorff, which I have not defined in this course so far, you can also think of Hausdorff space. Okay, these are all just to a kind of a jargon throwing. Okay, but once you understand what I want to say here, now what I'm assuming is F. So let us look at this. This is my F, okay, and this is my D. Okay, now I have two functions F and G. This is to R. Now what do I know? I'm assuming Fx equal to Gx for all x in D. That is, F and G agree on the set D, but not necessarily on x. You understand that? Then what do I want to conclude? I want to conclude F equal to G on x. That is, Fx equal to Gx for every x in capital X. As function, they are one and the same. Now, what is the advantage of this? You must have seen its analog in real analysis. If F and G are functions from R to R or interval in R to R, continuous function, if they agree on the rational points, then the functions coincide. Its analog is what we are trying to prove here. What all we need is dense set. The proof is exactly the same, so I will be brief. So let us look at the set E, set of all x in capital X, so that Fx equal to Gx. Right? What do I want to show? I want to show U equal to X. Because D is contained in this. Right? There are two ways of showing. Both ways are very interesting. I will show that. Okay. Now, suppose there exists X. Okay. Let, if possible, okay, x in X is such that Fx is not equal to Gx. Right? So let me say Fx in Gx. Okay, then what do? I can find 2. I do not know what is Fx, what is Gx. Okay, let's not worry about. Okay, this is my V1, this is my V2, and so that you can see V1 intersect V2 is empty. Can I do that? Now you can see that is where I am using its R, but I can also use any metric space. Or I can use what is known as Hausdorff space. If two distinct points are given, I can separate them by means of open sets. At least in the case of R, it's very clear, right? You had already seen such example, right? Now what do I know? I know F inverse of V1, that is U1, and F inverse of V2, okay, these are open because F is continuous. G. This is one is Fx, one is Gx. Okay, let me assume this is Fx. Okay, I need it. Okay, alright. Are you following? I am assuming Fx is less than Gx in the picture, but in the general metric space, suppose this is YD, then I will have this may be my Fx, this may be my Gx, this may be my open ball Pfxr, this may be my open ball B Gxr, so that their intersection is empty, etc., etc. Okay, I don't want to waste my time, and by now you should be very comfortable with this kind of notions, right? Now what do I know? Both are open sets because F and G are continuous, right? And X belong to both of them because Fx belong to V1, Gx belong to V2, right? Therefore, if I look U1 intersection U2, okay, this is non-empty set. Why it's non-empty? Because X belong to U1 as well as U2. Therefore, this is non-empty. This is a non-empty open set, right? You follow that? So therefore, this is a non-empty open set. Where? In X. What do I know about D? D is dense. Therefore, what do I know? There exists a Z in D intersection U. Correct? Because D is dense. But what do I know about F and G on D? Therefore, Fz must be equal to Gz because Z belongs to D. Since Z belongs to D and F and G agree on D, I have this. Follow? Right? Now, let's look at Z belongs to U and hence it's U1. This means Fs belongs to F of U1, which is V1. And similarly, F of Z belongs to F of U2, and that is UV2. That means Fz belongs to V1 intersection V2, which is empty set. So this is a contradiction. Therefore, what did I prove? Yeah, I proved that there is no such x. That means given any x in x, Fx must be equal to Gx. Do you understand this? So what are the ingredients of the proof? You should understand. What we did was we used the density of D and also that any two distinct points in R can be separated by means of open sets. So do you follow that? Therefore, this proof will work whenever F is from x to y and tau y, so that tau y has the property that any two distinct points y1, y2 in y, y1 not equal to y2, there exists a v1, v2 in tau y, so that yi belongs to vi and v1 intersection v2 is empty. Again, keep the picture in mind. If you know how to draw space, that's all it means. This is my y, so I have some y1 and I have some y2. Okay, this is y1. So I have an open set v1 and I have an open set v2. Their intersection is empty. This proof will work. And as an exercise, I want you to leave an exercise. Okay, use similar series. Okay, argument to show that the set E we define in the proof is a closed set. Okay, to show it's closed, what do you have to do? You have to show its complement is open. If x is in the complement, what does it mean? Fx. Okay, there is an x in the complement that says that Fx is not equal to Gx. Now you see the proof, right? Do you understand that? Please go through that. This is how you can master. Okay, don't be intimidated, feel confident, be courageous, go through the argument, you will see. Okay, E complement is open. That's essentially I have proved. Given an x is not in E, then we found a U so that x belongs to U, and that U has to completely contain in E complement. Okay, go through that argument anyway. Okay, accept this exercise for the moment. Then now I know by assumption D is a dense set on which F and G coincide. Therefore, D is a subset of E, and this is a closed set, and this is a subset of X. Right? Therefore, since the E is closed set, D closure must be contained in E, because D closure is the smallest closed subset of containing D. But since D is dense, I know D closure is X, and this is contained X. Therefore, what do I concluded? E equal to X. That means for every X in X, Fx equal to Gx. Okay, please review. Okay, as I said, do not worry about. Yeah, as I said, do not worry about remembering the proof. Okay, go with the flow, go with the thought process, keep thinking. If you do like that twice or thrice, you will see you yourself can naturally think on your own. You don't have to depend upon book or notes or anything. These are all very simple logical thinking. You can train yourself. Okay, I wish all of you will do that, or rather I hope all of you will do that. Okay, till we meet again, take care and stay safe.